Hi, and welcome to section 2 of scikit-learn recipes. In this section, we are going to take a look at dimensionality reduction. We're going to look at 4 different techniques of dimensionality reduction. The first technique is going to be principal components analysis. The second technique is TSNE. Third technique is factor analysis. And in the fourth technique, we will be looking at nonlinear dimensionality reduction using kernel principal components analysis. In the first video, we will be reducing the dimensions of our dataset using principal components analysis. To begin, let's open our Jupyter notebook and let's import all the packages that we will need to perform principal component analysis. So let's import PCA from scikit-learn, pandas, standard scalar again from scikit-learn. And these are packages that we've imported previously that I've just stayed here so that you guys can get used to seeing them as part of your Jupyter notebook. For the data, we're going to use the data that we used in the last section. So principal components analysis is impacted by the scale of the data. So we need to scale all of these numbers where the mean is equal to 0 and the variance is equal to 1. Because you see how these numbers are much larger than any of our other variables. This largeness will give an unfair advantage to these numbers and make it seem as if the opportunity amount in USD actually contains more information than any of the other variables do. So to scale the data, we're only going to scale our continuous features. We're going to use standard scalar to scale the data so that it has all the numbers have mean equal to 0 and standard deviation equal to 1. And this is good practice for data science projects, where you actually save the data set that you're going to use later so that you don't have to keep performing some sort of transformation to the data all over again the next time you need to use this data set. So I'm going to save this data as dimensionality reduction data so that I can use it again later on when we perform different types of dimensionality reduction techniques. To do a principal component analysis, you first have to figure out how many components you actually need. So the best way to sometimes do that is to check how much of the variance is explained by how many of the components. And when the variance explained sort of flattens out, that's where you decide how many components to pick for PCA. So as we can see here, after plotting the percent variance explained by each additional component, it sort of flattens out at 15. So in this case, we're going to look at 15 components. So we are going to reduce our data set from 19 observations or 18 without our predicting variable, and we're going to reduce it down to 15. So over here, opportunity result is the variable that we're trying to predict. So we remove that. We pick the number of components equal to 15. And then result is the number of components with the opportunity result. So that now we get our new model that has 15 components with all of the information that actually existed in the 18 components, also in these 15 components. Now let's run a logistic regression model with opportunity result as the y variable and all the other variables from this data set as the x variable. Now, when we run the model, our new model's accuracy is 0.82. If you remember, our previous model accuracy was 0.77. So this new data set with a fewer number of dimensions is actually more accurate than the previous data set that had a lot of dimensions. So this is often called the curse of dimensionality, where the more information that you have does not necessarily mean that your model will do really well. So if you want to understand more about how PCA works, this is a really good link to check that out. It gives you a great example of this is how the original data set looks. And this is what happens when principal component analysis is used to reduce the number of dimensions in the data set. So as we see over here, the number of dimensions have dropped from PC1 to PC2. There's also a 3D example of what the space looks like. And this is just a really good way to see what's actually happening behind principal component analysis.